Hey everyone, this is another short tutorial video on how to calculate an apparent dip when you have the true strike and dip of a plane or of a measurement of interest. So let's imagine you're drawing a cross section and you cannot draw that cross section perfectly perpendicular to the structural grain or to a particular measurement, for example. You will need to then calculate the apparent dip of that feature, again, that planar feature, for your cross-sectional view. So for example, here, a little sketch right here. So for example, here is a measurement of 210 degrees, 60 degrees, assuming that north is up on the page. Ideally, we would draw a cross section along this dashed line. Notice that it's perfectly parallel to the dip direction or perpendicular to the strike. But for example, if we had to draw our cross section along the A prime line, notice that we are not now perpendicular to that. But we know the orientation of this line, okay, which is roughly 285 degrees, because we can measure that directly off of our map. Okay, so let's imagine this scenario, and what we want to do is calculate what the apparent dip of this 60 degrees is so that we can accurately plot that on our cross section. Okay, so we're going to use our PowerPoint method, and so let's just jump into PowerPoint right now and take a look at how we're going to do that. So here's our layout that we have come to know and love. What we're interested in doing here is plotting that 210 60 degree measurement. All right. And we know this is our, let's call it our feature of interest. Okay. Bed, fault, dike orientation, whatever it might be. All right. And that's the true strike and dip of that feature of interest. And our cross section line, we've measured directly off our map, and we know it's 285 degrees. And of course, when we're drawing a cross section, we're drawing a perfectly vertical slice. So we know the dip of that cross section line is 90 degrees. And this we will just call our cross section line. So now let's, and I'm actually just going to keep this clear, and I'm going to make this blue. So we'll draw our feature of interest in red and our cross-section line in blue. So let's get started. Here we are in PowerPoint. Notice I already have my little star over here to make sure that I measure in on my from the primitive, starting from this side. And so now let's just go ahead and rotate our cross-section. And we do that and go to Arrange, Rotate. Oops, I haven't selected it yet. So there we go. Select it. Arrange, rotate, more rotation options. And again, we could have manually rotated this, but why not use the power of software? And of course, our first plane is 210 degrees strike. All right. And now I'm just going to zoom in so that I can see this a little bit more clearly, and so that you can see it a little bit more clearly. And I'm going to draw my plane at 60 degrees dip. So I'm going to insert my curve. I'll change its color afterwards, but again, we start from here. And recall that we want to be coming in from down on this side, and we are going 60 degrees. So 10, 20, 30, 40, 50, 60 degrees. There. Another click here, keeping our line relatively straight. And finishing it up there with a double click. And I'm just going to quickly change that to red so that for clarity when we look back, and I'm going to just make it a little bit thinner. And I will zoom out right now back to 100%, and I will rotate back to 0 just so we can see the orientation of that plane. And you can again see 210 60 degrees. So now We've measured that. We know what its true dip is at 60 degrees. Now what we want to do is figure out the apparent dip. And the way we're doing that is we're just going to draw our line of cross section at 285.90, and where that intersects our line, we're going to be, it's going to make a point, and we're going to be able to measure the angle of that of the dip of that angle, which will be our apparent dip. So let's go ahead and do that. I'm going to rotate again to 285. There's our measurement, and again, we always want to measure in from this side. I'm going to zoom back in here. 170. So we're in here. We're again measuring in from this side, and fantastically, since this is vertical, we are going to insert a line, curve, and in fact, it's going to go from here straight through the primitive, or excuse me, straight down to the other side, to the other primitive, because it is perfectly vertical. This is a perfectly vertical line. And there it is. I'm just going to make it a little thinner. All right, so there's our blue line. Okay, so now all we need to do is we can actually just measure down. I'm going to like take the rotation out of this so we can see it. And we'll do that here. Rotate 0 degrees. And there is our line. Okay, now all we have to do is just measure down this line. So ideally, we would have actually just left it the way it was, but we can just now just take and I'm just going to zoom out a smidge. And I'm going to rotate such that my line, I might as well just use the rotation direction. So might as well rotate 285. Again, you wouldn't have to unrotate and zoom out. I'm doing this for the video. So once you've actually done this, you are good to go. So now what you can do is you can count down this line. Sorry for the little jitter there. I just had to pause recording to just grab a quick little drink. But where we sit right now is I've rotated our cross-section line back to 285. And again, you would not have needed to do that. I only rotated back to north so that I could demonstrate and show what this looked like. But you would be able to just draw this line, and now you can do what you can do is you can count from the primitive to the intersection here, the angle, which is 10, 20, 30, 40, 50, 2, 4, 6, 8, 9. Okay, so this angle right here is now 59 degrees. So if we go back to 0, and I'll just zoom out to 100% here. And our cross-section line, so our apparent dip is 59 degrees. All right. And we can also see that it is to the west. Okay, that's to the west. We have a west dip, and that's because our dip is over here. Okay, so our if our intersection was in this side of the hemisphere, we would actually have an easterly dip. Okay, so when you're drawing your cross section, you now know whether it should have an east or a west dip. Although you already know that it's a west dip because the 210/60 is not that different. Now, there's not a tremendous difference between this 60-degree dip and this 59-degree dip in this example, but be aware that with shallower planes, so if your feature of interest, your dike, your bed, your fault, whatever it might be, has a shallower dip, and or your cross-section line is more off of the orthogonal to that dip direction, you can have much larger discrepancies between your true dip, okay, and your apparent dip. So you can have 5, 10, or even 15 degrees difference, which will make a massive difference if it's 5, 10 degrees on your cross-section in terms of that dip angle. And you want to be accurate in reflecting that. So that is calculating the apparent dip from the true dip. Using stereonet. It's fairly quick and easy to do, and so hope that helps you out.